What's up, sim scientists? You thought we were done. We ain't done. We ain't done. All right, we got one more exam to go. We got 7th period. Gonna kill it tomorrow. And I'm getting some fan mail. It's about time. All right, a couple topics to go over. First of all, electron configurations. Let's review. All right, so I got my sketch of the periodic table here. First thing with electron configurations, we got our different suborbitals, our different orbitals, our different blocks on the periodic table. So here I have the S block, gang. Okay, S. Then in the middle here, I have D, the D orbital. And over here, I have the P orbital. Now there is also F. We're not going to worry about F. F doesn't matter. So S, D, and P. So that's how we break up the periodic table, and we can do that here as well. Here's S. It's kind of hard to see. Here's D, and here is P. Hopefully you see how that correlates to what we just wrote. Okay, so when we write an electron configuration, the first number is the energy level. So over here in green on the side of the periodic table, I wrote the energy levels. Okay, so that's just periods, the period number. Periods go across, groups go up and down. So energy level 1, 2, 3, 4, 5. This is all going across. Okay? So when we write out our electron configuration, let's write out the electron configuration of helium, or hydrogen. So what's the energy level? 1. So this first number here is the energy level. Corresponds to these numbers. So for helium, or hydrogen and helium, but for hydrogen, it's 1. Now the second thing in here is going to be the letter of the block. So which block is hydrogen in? Well, it's in the S block. So it's going to be 1s. So this is the orbital shape. The orbital shape of the electrons. So we talked about S's are spherical orbitals with 2 electrons in it. P is the dumbbell shape. And you can have the 3 different orientations of the dumbbell with 2 electrons in each. And then D is like that, but with 1,000,000. So that's what we're talking about with the letter, but it corresponds to the block on the periodic table. So if you know your 3 blocks, then you know that this for hydrogen is going to be S. Now, lastly, we have the exponent number. That's the number of electrons. It's also the number in order as you count across the block. So what do I mean by that? Well, we can start numbering our elements across the block. So we can have 1 here, 2 here. Then we go to D, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These numbers are going down the groups, okay? So anything in one period is going to have the same number as the other ones because it has the same number of valence electrons. Now we come over to P, and we have 1, 2, 3, 4, 5, 6. Okay, so for hydrogen, it's in the S. It's in the first energy level in the S block, and it's first. It has 1 electron. So 1. Now, when we do the long electron configurations, if we add up these numbers, we get the total number of electrons in the atom. And if we add up these numbers in the highest energy level, we get the valence electrons because valence electrons are electrons in the outermost to highest energy level. So this is number of electrons. So that's how these numbers break down. Now, if we're doing configuration, so let's do the electron configuration of, let's do selenium. Selenium right there. So that's my target. That's what I need to get to is selenium. Okay, I'm going to write it right here. Okay, so selenium. So when we're doing electron configuration, we start like we're reading a book at the top left. We're going to start with hydrogen, and we're going to go across. So we start with 1. We're in the first energy level. First, we're in the S orbital. Okay, so we have hydrogen's 1s1, like we wrote up there. We go across here to helium, which is the exception to the block rule. Helium's in the S block, even though it's over here. So it's 1s, 1s1 for hydrogen, 1s2 for helium. So it's 1s2. Okay, now like reading a book, we go down to the next energy level. So now we're over here at lithium. Okay, so we are in the second energy level. Now we're at 2, still in the S block, 2s. Lithium would be 2s1, beryllium would be 2s2. So the S block can fit 2 electrons in it, whether you're here or here or here or here or here. The S block's going to fit 2 electrons in it. Okay, now we go from 2s across, and we're over here now. We're still in the second energy level, but now we're in what block? the p block. So we had 2s, now we have 2p, and then we're going all the way across because we're trying to get down here. So 1, 2, 3, 4, 5, 6. 2p6. Okay, now we go down to the next energy level, 3. We start with S. Okay, so we're going down, we're reading across. 3s. It's going to be full, so 3s2. No matter where the S block is, if it's full, it has 2. And we go across to P. So we're still in the third energy level, but now we're in the P block, 3p. And again, we're going 1, 2, 3, 4, 5, 6. All the way across, 3p6. Now we go down to fourth energy level. We're 4, back in S. 4s, 1, 2, 4s2. And we go, now we hit the D block, right here. Now we're entering the D block. The biggest hindrance for this, once you get the hang of it, is to remember, is this 4D? No, it's 3D. We start with 3D. The D block is always one behind the period that it's in. Okay, S and P, the S and P block, S and P make up all the valence electrons. How many valence electrons does every atom want to have? 8. How many are in the S? 2. How many are in the P? 6. 8 total. So the D block cannot be the outermost energy level. Therefore, it has to be below the outermost energy level. So we're in the fourth energy level. That's our highest energy level. The D atom electrons have to fill in the D, or the third energy level. Okay, so we go back. So now we're in the D. It's 3D, and we go all the way across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3D10. I need a little extra room here. Okay, so now we go through D, and we're back at P, which matches the period number. So we're back in the fourth energy level, 4, and we're in P, and we have to get to selenium. So P1, 2, 3, 4. 4. And that's the electron configuration for selenium. So you'll notice anything in its same group is going to have the same final letter and number. What's going to change is the energy level. So the final thing for selenium, the final thing for selenium is 4p4. For sulfur, it'd be 3p4, and for oxygen, it'd be 2p4. All right. So that's how we do it. We read like a book. We go from top left across and down, and we write it all out. Okay. So how many valence electrons does selenium have? Well, if we look at the electron configuration, for that outermost energy level, we have 4 here and 4 here. So then we look at the exponents. 2 here, 4 here. 4 plus 2, 6. 6 valence electrons. We also can just count across 1, 2, 3, 4, 5, 6, 7, 8. Don't forget that. That's a quick way to figure out valence electrons. So that's that. That's how you figure out the electron configuration. It's really easy to practice on your own. Just pick an element. Pick chlorine and try to write it out. Then Google electron configuration of chlorine, see if you got it right. Or tin, or tellurium, whatever you may want to do. Okay, so hopefully that clears up. Keep in mind what these 3 things mean, what we're doing. Read it like a book. 1s2, 2s2, 2p. The other thing is, every time you go to a new number, you add a new letter. So, let's use this. So for 1, we just have S. For 2, we have S and P. For 3, we have S, we have P, and then we add D in the third. So we don't skip to 4 for D, even though it's in the fourth energy level, we add D there. And then F would be added in the fourth. But that's one way to remember that 3D happens, and you can't forget about that. 3D. Now, another thing to go over real quick are the energy diagrams. Okay, this was the last thing in the review. So if you have an energy diagram like this, okay, what are we looking at here? So on this axis is energy. Okay, so this is 0, and this is 5, and this is 10. So they're real simple. These are your reactants, the potential energy of your reactants. Here's the potential energy of your products. Okay, so you have reactants, you have products. Now the reaction happens. It takes energy for the reaction to happen. Okay, so it takes energy to get here. That's your activation energy. So in this case, from 5 to 10, the activation energy is 5 because you're going from 5 to 10. So the difference here. Yeah. I'm making a video. Oh, okay. Anyway, so that would be your activation energy here with a value of 5. The potential energy of your products is 5. Your reactants, the potential energy of your products is 10. So is this endothermic or exothermic? We went from 5 to 10, so it's endo because you gained energy. And is there anything else to touch on here? This is just time. This is as the reaction progresses. If it were the opposite way around, if it went like this, that'd be exo, you're releasing energy. Yeah, I think that's pretty much it. I mean, this from here to here is the energy released when the products form, and from here to here is energy gained. So it's the activation energy from here to here, how much energy it takes to get this reaction to happen. And yeah, that's pretty much it. Just a quick review on that. So hopefully that cleared up electron configurations and helped to refresh on potential energy diagrams. Good luck tomorrow.